Okay, I'm pleased to present second session of WITS. Artem will tell us about retrofitting null-safety into Java. Please take it away.
And can I use the mic?
Your mic too.
Oh, hello. Just, yeah. 1, 2, 1, 2. All right. Hi all, my name is Artem. I work as a software engineer at Meta. And in this talk, I will tell you a bit about the work that we did to turn millions of lines of production unsafe Java code into beautiful null-safe Java code. So I guess before I start, I would like to thank the program committee for the opportunity to speak here alongside such an amazing group of people. And when I did this talk internally a couple of weeks ago, I received a somewhat puzzling advice from my colleagues who are more familiar with the Popl audience. And they said, cut the technical details and just add industrial context. And I was like, all right, let's see how it goes. So let's get started. So when it comes to null pointers, there are kind of two perspectives. So perspective one is the runtime perspective, which is basically when you want to dereference a non-primitive value, you check it, whether it's null. If it's not great, you invoke a method or something. But if it is null, you get a null pointer exception. Your backend service crashes, your applications crash, and users are unhappy, with this experience. But from the developer's point of view, things are more complicated. So as a developer, you get all these questions like, can I get null here? Do I want to accept null, or maybe check for null, or assert that it's not null, stuff like that. And this is a lot of decision making just for kind of one dereference. And so if you multiply it by a million times, there's just a lot of overhead. So basically, it's not having this implicit nullness is not very efficient, and it's not safe. So naturally, there's this question, there has to be a better way, right? And that's what we did internally. So basically, over the course of, let's say, 3 years, give or take, we migrated millions of lines of our production Java code to null-safe Java. We developed tools, deployed them at meta scale. We iterated on the analysis and got some really nice benefits. This is a work of many people, including my close collaborators, Ilya and Dmitry, but also of the extended null-safe team, which is hundreds of developers that actually drove the adoption of null-safety within their teams and orgs. All right. So when it comes to the structure of this talk, there are 3 parts: inception, scaling, and hardening. And this it kind of reflects our own journey. And so I guess for me personally, hardening is the most interesting. That's where we had to teach our system to understand generics, to work with generics, to add contracts, to figure out how to produce comprehensible diagnostics, and so on and so forth. But let's start with inception. I'll have to skip a lot of context here, but 2 main pieces were that at that time it was known that null pointers are a problem, right? We also knew that something like an optional type, as you see in Camel or Java or Rust, is really not a solution in Java because of this picture and some other problems with the optional. And lastly, Meta had a history of turning dynamically typed languages into statically typed languages. So after thinking for a little while, I came up with this project idea, which I very ambitiously called 0NP. I was very naive at the time. And so the idea was to take this unsafe default Java, like the code base, from this state into a state where it's all beautiful null-safe. And I mean, of course, when you talk about these massive code transformations, it's important to have some process in place. And so this process looks something like this. So we just, we fix a class, we make sure it is compliant with the checker, has 0 issues. We slap a null-safe annotation on top of it. And then we enforce at, like CI time, that you cannot introduce any more errors in an already clean class, otherwise we will break your build. And so you repeat this multiple times, and you get to something like 90%, right? And so this had 2 very nice properties in a sense that it was we had a very clear progress metric, And we also had, I mean, the progress was monotonic. As soon as something is null safe, it stays null safe, right? And I mean, this plan may seem a little bit like this meme, but nevertheless, like this idea, I pitched it, it landed well, and like with a few collaborators, we started working on it. So to kind of do this, we had to change the vocabulary of types. So string now means non-nullable string, and nullable string means, you know, the default Java's nullable string. We also had non-null and unknown, but I will get to them later. We also really needed flow-sensitive typing because all the code in Java is written with the, like, using these explicit control structures. So whatever type checker we come up with had to understand control flow very well. And I mean, flow-sensitive typing is not very common. There are few languages, relatively few, that actually do this. So it was like not super obvious at the beginning, but luckily, you know, these, as many other problems, can be solved with AI, and that's actually what we did. Of course, here I'm referring to the proper kind of AI, and so the idea was that, yeah, we just take the code, we turn it into a CFG where the control flow is explicit, we run our AI analysis on top of it, and this kind of gives us this flow sensitivity sort of for free. And also, as Kuzo showed in 97, types are just abstract interpretations, so this all kind of made total sense. So to the scaling part, here I will front load some of the industrial context that I mentioned before. So first of all, we had these constraints about scale. So right, it's a multi-million line code base, and that's just first-party code. When you had third-party, it's just mind-boggling. We had thousands of developers that are submitting changes every day. So, I mean, this is a blessing and a curse at the same time, because, I mean, in this code base, you can probably find all possible combinations of Java feature usage. So it really gave us a lot to work with. Then there was this constraint about timing and impact. We couldn't really disappear for 2 years to come up with this grand unified theory of nullness in Java. We really had to deliver the value incrementally and ship changes to production code from the get-go. And finally, we had to smoothly integrate into the developer's workflow. And I would like to elaborate on the last point a little bit. So from the developer's perspective, they like to solve business problems, ship impact, and write good code, probably in this particular order. What they don't like is when things slow them down without a very clear benefit. So like friction is a very important consideration like for all of this. So what we actually had to do, we had to increase developers' velocity while allowing them to ship safer code. And so the type checker itself is a very important component. It's like the central in this whole thing, but it's not the whole thing. There are also other, like many other components that had to be implemented, like CI integrations, CLI tools, ID integrations, tools to work with the user-defined models, and so on and so forth. And in particular, something like cloud build integrations took a little while to get it up and running, but in the end, we could kind of retype check the whole code base in something like 10 minutes, which was extremely helpful to iterate on the analysis and understand kind of the impact of our changes that we were when we were experimenting with the type checker. So a starting point was Infer, which is a platform for static analysis. It does compositional, interprocedural, summary-based analysis. It has support for many languages, including Java. So at the time, there was this checker called Eradicate, which did a simple nullness analysis, and it was also intra-procedural, and so we wanted to stick with this just for the scaling and understandability point of view. And so the good thing about AI is that like you can really dial in the complexity by choosing the right abstract domain. So like you can start with something as simple as this, where it's just either non-null or nullable. And that's what we actually started with. Kind of quickly, we had to extend it further with these other elements of the lattice, like null, bottom, and unknown, so that we can reason about feasible and infeasible paths and deal with legacy code. And so we actually learned a lot during the scaling phase, especially about how to run this giant code transformation so that you can actually start this transformation from anywhere in the code base, but also so that at each step the system is consistent. But this had not much to do with the actual kind of type system things. So I tried to sample 2 learnings that had to do something with the type systems. So the first one is about soundness. Very important. No questions about that. Before I see pitchforks, yes, very important for a type system to have soundness. But also, it adds a lot of friction if you just go to the extreme. So like in this example, let's say you null check the field, then you call a method on this field, but there is this method call in between. So if you want to be sound in Java, you would just reset whatever refinements you did at this program point. Because this method could reassign the value to a field. So this is bad, and this adds a lot of friction, and we couldn't really afford this. So what we did instead, we assumed that all Java methods are pure, which may be appealing to the Haskell programmers here. But it was also appealing to our developers because they didn't have the kind of friction that they would have otherwise. And then there was this paper by people from Nullaway where they corroborated our own experience with this soundness and unsoundness, or how to strategically add unsoundness to the system so that it's still fine in the end.
I love the idea of a targeted unsound assumption.
Yes.
Great phrase. Remember.
Thank you. So the second thing I would like to mention is, so when you see this piece of code, and you see this null check, and bar here means non-nullable bar, you probably think, all right, so that's infeasible path. And the first instinct of compiler engineers when they see infeasible paths is assume that this is dead code. So let's just remove the dead code, which may actually be a pretty bad idea because there may be a bunch of callers that actually call this code with null value, and that's because the whole code base is in a flux, right? So this code may actually be undead. I guess the more constructive way to deal with these situations is to instead just change the signature if the rest of the method actually allows it, so that you turn this infeasible path into a feasible path, but also type check all these calls so they don't produce an error. So now I would like to switch to the hardening phase, which is basically where we started working with hundreds of developers, very closely with library authors and framework authors, so that they can improve the UX and safety of their frameworks. So at that point, about half of the code base was in this null-safe state, half was still in flux. And also, developers started writing more generic Java code, more sophisticated code. They wanted better guarantees. And we also started getting more Kotlin code with nullable generics. So at that point, it became clear that we kind of need to support the full extent of Java language features, including generics. And this way, Nullsafe was born. So we could not extend, it was difficult to extend infer to support the full generic Java type system. So we actually re-implemented this thing from scratch as a Java compiler plugin. Nullsafe has a bunch of things, including a complementary object initialization analysis, but I will focus only on the type checking bits. So Java is actually a very large language. It has a lot of features and also intersections between features. So when you add, this explicit nullness, there are many details that you need to get right. And so here I would like to mention this project called JSpecify, which was kicked off in 2019 by Google and JetBrains, and then more companies joined in, including Meta. And it kind of, gets these details right. But just, from the implementer's point of view, that's how we extended our type system, from the simple nullness lattice to, the full generic system where we just basically attach this nullness lattice to type components. So we have a new type system, like a type lattice in our generic null-safe, and this allows us to actually properly type check generic Java. It works well, but there is one complication, and that's error messages can be really hard to follow. So you have this complex type system, you have flow-sensitive typing. So when you have something like this, nullable string cannot be converted to a string. Even in this small snippet of code, it may take a while to figure out why exactly it happened to be, this particular error message. right? And if you show this error message to a busy developer, that's probably going to be their reaction. So we couldn't really do this. We had to do much better than this. And so we had to extend our abstract domain to this sort of type trees, where the structure of the tree sort of reflects the provenance of the type. So, for instance, when you have this getObject method call, you'd get a terminal type with a reference to this method call. When you have a instance of check, you would get a refined type that points to the underlying terminal type. And when the control flow joins here, you would get a joined type that points to its components. And so this allowed us to kind of produce nice error messages with a trace that points to the right place where things went wrong. And like in this small snippet, this is, again, probably not, the trace is just one line, and it's really easy to understand. But in a real production method of 300 lines, these traces can get longer, but also much more helpful than in this case. Now, when you go from this simple nullness to generic nullness, method calls become much more complicated, like handling method calls. So in here, I would like to talk about the constraint solving and contracts. So when it comes to constraint solving, that's your usual stuff. So you have generic method, you have your arguments, you generate constraints, you simplify them, and then you have a solution, and you instantiate your inference variables. So that's your regular stuff, nothing interesting here so far. But when it comes to, this particular snippet of code, with forward analysis, you would first infer the type of the right-hand side, and then you would see what the left-hand side is and whether they are compatible or not. So this means that we would generate this set of constraint, right? We would infer that T here is just equal to a bird. And this means that the right-hand side would be a list of birds, and a list of birds is not a subtype of a list of nullable bird, because Java generics are invariant. So this means we would reject this code, which is actually pretty terrible. So we had to do better than this. And this is actually a kind of a known technique. I think Pierce described it in '98 in one of his papers. But the idea is that we look at the assignment context, and we add some additional constraints here about the desired type that we want this whole thing to be. And so this way, when we solve the constraints, we get that T is a nullable bird, everything type checks. So previously, we would just solve these constraints a bit too early, and this way, we get the full context and a nice solution. Now I would like to switch to contracts. And contracts are funny because they are usually these helper methods that developers use a lot. And without understanding what these helper methods do, you can't really accept correct code. So with contracts, you accept more correct code, which means you have less friction for developers. And so examples of contracts would be something like get.default, where if the default is not null, the result is also going to be not null. Here, you can probably rewrite this method as a generic method. But developers don't want to do this. They want to see this simple signature with a kind of this implicit contract attached to it. Another example, this check state method that throws if the argument is false. And an example usage may look something like this, where this Boolean value is just a bunch of null checks. So after this succeeds, at the next program point, A, B, and C should be refined as non-nullable. So what we do here is, again, probably not surprising, we do set solving for contracts. We translate contracts into formulas. Refinements are obtained from formulas fixed assignments, also known as backbone or frozen variables. And this works both for the result and the arguments of these methods. So when it comes to fixed assignments, there are many ways to calculate fixed assignments. That's probably the easiest one, and that's what we started with. You just check that some formula is unset, which, again, there are more efficient ways, but this also works, and it's very easy to implement. So just reflecting on the contracts and set solving in type inference, there are pros and cons, of course. So the pros are that this is a principled solution, and you can actually extend it. You can also apply the same set solving to, let's say, to reason about feasible and unfeasible paths with these type trees. So there are lots of applications. But like even for contracts, we had zero problems with it. It just worked, and even a baby set solver was performant enough. Yep, thank you. Because the formulas turned out to be rather small, at least in production. And so the initial version actually took just around a week to implement. So that was all very nice. The con is that when you first talk about it, it may sound like a crazy enterprise, but it actually turned out rather well. So now I would like to conclude with some discussion around reliability and productivity impact of these changes. And so here, I have the numbers for our Instagram, Android app. And so, like when you see these columns for the alpha channel, beta channel, and production. So alpha channel is this pre-release version that is just enabled for a small fraction of users. Production is the current release that is enabled for billions of users. All right, so when we look at the alpha channel numbers, we see this significant drop, like 3 times less null pointer exceptions in the alpha channel. So this basically means that developers started making much less silly null pointer exceptions, like NPE mistakes, and spend less time fixing NPE mistakes that happen in production. So this is direct reflection of improved developer productivity. Now, when it comes to production, as I learned over the years, real-world reliability is a lot more complex than just the type safety of, let's say, the client code. So when we were working with teams, particular teams, on improving null safety of their parts of the code base, they reported numbers ranging from 35 to 80% reduction in the volume of NPEs. But like for the whole app, on average, we measured it at minus 27%, which actually is very substantial. If you slash a third of NPEs, you get many, many more users that are happy with the app and spend more time there. So overall, we were very happy with the results. But again, the real-world reliability is complex. You have also like all these sorts of interactions between systems. You have things like reflection, JNI, and whatnot. So that's, I would say, a different story. And I would like to conclude with an inspirational quote of mine, and that's the quote. We couldn't imagine how much work we would have to do to reach our goal that we stated initially, but still it was very rewarding. So I'm very happy about what we achieved. So thank you very much for your attention.
All right, we have time for questions.
I'm curious how this works with constructing new objects. Like Java objects are all born full of nulls, and the constructor has to try and fill in some or all of the fields with nulls. So how do you track what's null and what's not null, especially when there's methods being called from inside a constructor when the object is half built?
Yeah, so we have this initialization analysis that I mentioned before that is complementary. It's an interprocedural analysis, so we look into these methods that are called inside a constructor to see what they actually initialize. And I mean, of course, there are again like false positives in this analysis. Like there's a sound approach, I think, called freedom before commitment, which is type-based, but it adds a lot of annotations, and we couldn't do this. So we had to build our own kind of custom thing, which again, like for our use case, worked well. But you can construct these examples where you either leak this or do something funny where it would break. But like overall, yeah, that's how we do it.
Thanks.
Very interesting talk.
Thank you.
I'd like to know, so null pointer exceptions have been a problem since forever, basically. I'm really interested to what do you think made this possible? Like, was it a change in Java or in your company? What do you think was the kind of the the cause that you have to do this?
Right. I mean, that's a very good question, in a sense that no one actually asked for this, but everyone wanted it. So what we had to do is just to come up with a reasonable project that you could, again, like pitch and that the leadership would understand, and then just, burn down this chart of non-null safe things. But I would say it's mostly about the organizational aspects rather than the technology in particular.
Okay, thank you.
Thanks. When you're talking about undead code, right? That slide. I love the zombie illustration. So I could imagine that a function in existing code that tests for null might have two cases. It might be a situation in which null is really a perfectly legitimate argument and you're testing for it, or it might be that really null is very bad, but the programmer was programming defensively, right? So then you still have to leave that defensive test there, is because of there might be part of the code base you haven't converted, or because some of your targeted unsound assumptions were actually wrong in a particular case. Okay, so you want to leave it there. But nevertheless, the question is, when you're looking at the code with the if in it, does your system say, oh, you meant this to be non-nullable, I better check that? Or does it say, oh, you've got a test there, so null is just fine? Which of the two? Or do you rely on a human being to tell?
So we definitely rely on human beings to some extent, but also if there's an explicit null check, so let's say you have if A equals to null, even though the input type was not nullable, we would assume that inside this branch, it is null. So we trust the actual sort of behavior that it would be exhibited at runtime. It actually, it's make the whole thing a bit more complex, because when the control flow joins, if you just do it in a simple way, before you had a non-null A, then you refine it to null inside the branch, then control flow joins, you join non-null and null, you get a nullable. So the rest of the method gets poisoned by this decision, so we had to kind of have some workarounds for this. But overall, yes, we tried really hard to, like when we see an explicit null check, we refine it as it would be at runtime.
James Noble, creative stuff. I was just going to say, but I guess the point here is you're actually working in a closed system.
Yes.
So really, you're just working on the Android app. So
or apps.
Or apps. Right, but all from the same company. So in the future, you expect all the code you're handling is going to pass not just the Java type checker, but also the non-null checker. So you won't have people, for example, who are writing against a public API, where you can't be sure that they are writing a null checker, and so even if you annotate your method argument with non-null, that will be observed by the client, but you don't have that case.
Yeah, I mean that's an important consideration for sure. So like on one hand, we when we consume this external third-party code, we enforce that developers should provide an explicit signature. So that's kind of this thing about user-defined models. When it comes to other people consuming our open source libraries, I mean, this is complicated, right? So they are annotated with, as we think, clear semantics. Whether they would like to respect it in their own apps, I mean, we're not really responsible for this. But there is definitely this, the JSpecify thing. It is this attempt to produce this kind of standard semantics for nulls in Java, so that open source libraries from Google can have these consistent annotations from Meta, from other kind of major players. I guess like one thing to mention here is that we implemented this solution because we could do it at the time. It was viable. Java itself would probably implement a different solution. It seems that they're, maybe like in 5-10 years, it probably will be something different, but time will tell.
Okay, because we're at 11:30 and a bunch of people have entered, I want to remind everyone that and inform everyone, the second talk of the session has been canceled. We had to cancel it. Sorry if you're here for that talk. But since we have a lot more questions, I'm going to keep going. And I'll remind you that the next talk of the session starts at noon. Simon still has to work on his slides. I've seen him.
So I really liked the description of error messages because when you have any sort of flow-sensitive typing or subtyping in particular, you soon stop being able to get away with pretending errors of a single location. You need at least, here's where the null came from, and here's where it went that wasn't allowed to go. And I'm wondering, do you have any idea how much value your users are getting out of the bit in the middle? Would they be happy with just the here's where it came from and here's where it went? Or are you producing the full trace of, and then it was assigned to this variable and then it went to here and to here and to here? And if so, is that bit in the middle very useful?
I think it is very useful. It's like going from very bad experience to okay experience. So like even having this would be, it would be great. But obviously, like as you have more things like, contracts and stuff like that do these refinements in a very weird way, having a more complex, like complete trace is kind of this next step to get from good to great experience.
Very cool.
Thank you.
You briefly mentioned JNI, and I see that your null-safety system kind of reminds me of a refinement type system where you can say X such that X is not null. Is there some appetite or is there some plan to tackle interacting with native code? I see that this is a... Right, I'll let you keep going on with that.
It's been floating for quite a few years. Maybe you should better ask my colleague Jules about this. Because that's something that we could potentially tackle with infer, because it's multilingual, right? So we can analyze both the Java and the C++ side of things and see whether the contracts on the boundary holds. But we didn't get to it yet.
Hi, thanks for a very nice talk. And
Thank you.
I have a question about the Instagram app, like the diagram. What's 100%? Maybe you said it. I'm sorry, I missed it. So what's the total thing? Is that the number of the total report or the number of?
So this is a relative percent of NPE crashes. So we take all the crashes and we see like what portion is caused by null pointer exceptions. So this is just percent. I cannot show the absolute numbers.
Okay.
So piggybacking off Simon's question about defensive programming versus, cases where null is legitimate.
Yeah.
It sort of seems like a gradual typing problem. Like I want to sort of specify that part of this is nullable, and then, like that change sort of flows through my program. And so maybe I just missed it, but in your description, so when I'm writing a function, as the developer, am I responsible for going and checking all of the call sites before I can delete my null handling branch, or how does the change propagate through the code base?
Very good question. Yes. So if you want to make a breaking change, so let's say previously your return type was not null and now it's nullable, you will not be able to land your change unless you fix the callers. So that's like one of the benefits of this closed world ecosystem, where we can actually automate this to a large extent. Again, like it's not something that you would probably do manually, but you can either do it like in multiple steps or with the use of automation. But that's, again, people understand these sort of considerations. So if some API is used very frequently, are again like very conscious about the blast radius, so to say. And I briefly mentioned what we learned about like how to make sure that the system is consistent, although you can start null safing from everywhere. So before we actually released it to the wild, what we did the analysis of the most used APIs, right? And then we made sure that these APIs were properly annotated. And this way we can try to mitigate the problem where at some point your system evolves in two different branches, where one thinks that it's not null, the other thinks it's nullable, and you cannot quite reconcile it.
Thanks. What with the whole tracing that you added to the type system and the set solving that you also added, what is the performance impact on type checking or on compilation?
Very good question. Very dependent on like how pathological your case is. Like usually the impact is not large, but I mean if you have like a generated piece of code with 2,000 lines of switches, may be problematic, yes. So we saw something like 10x worse than what you would, your Java would give you. But again,
Any more questions? Okay, then let's thank our speaker one more time.
thank you.